Okay, so we're talking about work and energy, and the story here is that suppose you have an object experiencing a force, and that force happens to the object during a displacement that it's being displaced. And suppose the force is being directed at some angle theta, then we say that the work done by the force F as the object is displacing the displacement S is equal to the force times the displacement times cosine the angle between the force and the displacement. This here is the magnitude of the force. This here is the magnitude of the displacement. And this theta here, angle between the two directions, the force and the displacement. And this here is called the work done by F on the object as it displaces displacement S. So this is the first part of the story. And then if you think about multiple forces applying to that object, suppose an object here is being subject to multiple forces, and it's displaced a displacement S. By displaced, of course, it means that it starts at this location and ends at this other location here. And so the object starts over there, is the initial situation, and this is some sort of final situation. So it gets displaced, this displacement. And of course, here we're assuming that the forces are constant and that the displacement is, along a straight line. Then we can always say that the work done by each of the forces is, so the work done by the force F1 is equal to the magnitude of F1 times the magnitude of the displacement times cosine the angle between the force and the displacement. And the work done by force 2 is F2 times the displacement times cosine the angle. So each one has ... 3 is the same thing, right? So for each one, you calculate the work done by that force by saying it's the magnitude of the force times the magnitude of the displacement times cosine the angle between the displacement and the force. And the sum of all of that is whole work. 1, 2, 3, and if there's more, you add more. That's called the total work, sometimes also known as the net work. Now, each work could be positive, could be negative, or could be exactly 0, and that depends on the cosine function. Because if you remember, the cosine function looks something like this. This is cosine theta, if this is theta. When theta is 0, the cosine is 1. When theta is 90, the cosine is 0. And when theta is 180, the cosine is -1. So the work is positive if the force and the displacement make an acute angle like this. The work is 0 if the force and the displacement are exactly 90 degrees from each other. The work is negative if the force and the displacement make an obtuse angle like that. So if theta is less than 90, then the work would be positive. If theta is exactly 90, then the work would be 0. If theta is somewhere between 90 and 180, then the work would be negative. So the work is a scalar quantity, so it could be positive, negative, or 0 with units. It's called joules. Now, it turns out this quantity here, the total work, was a really useful quantity. And we'll come back to that after we talk about something called the kinetic energy. So the kinetic energy is the energy associated with an object of mass m moving with speed v. Then I can always say that the kinetic energy of the object is defined as half its mass times its speed squared. So you can see the more massive the object, the bigger the kinetic energy. The faster the object is moving, the bigger its kinetic energy. Kinetic energy is basically a quantity that quantifies how much energy is associated with the motion of an object. And again, it's a scalar quantity, meaning that it has no direction, and its units is also joules. But the difference, now linking the two ideas together, we find out something called the work energy theorem, or the work energy principle. And the work energy theorem says that if I have an object with a bunch of forces acting on it, and it ends up being displaced at displacement S, then I can always say that the total work done on that object during its displacement is equal to the change in the kinetic energy of the object. So if this is situation 1 and this is situation 2, then the change in the kinetic energy means kinetic energy final minus kinetic energy initial. And this is the total work done by all the forces acting on the object during the displacement. You know, it's something really interesting that is happening here. And the analogy that I like to think about is, so suppose you have a bank account, you know, you wake up in the morning and the bank account, let's say, has, you know, like $100 in it. And then you do some transactions. Maybe, you know, you spend some money for a drink or a smoothie or something, and then you spend some other money for gas, you know, whatever you do. And then maybe you get in some credits from work or something, so some sort of salary or anything like that. So you have debits and credits that are happening. And then at the end of the day, you find that the account is at a different balance. So the balance that you started with, that corresponds to, in my mind, in the analogy that I'm thinking about, this balance that you started with, that's the kinetic energy at the beginning. The balance that you ended with, that's the kinetic energy at the end. And then all of these transactions, all of the stuff that happened in the middle right here, that's the work done. So you say the work done, these are all of the transactions that are happening, whether positive or negative. They keep adding to the account or taking away from the account. And that's equal to the change in the balance. What did I have at the beginning and what do I have at the end? The difference between them, that's what happened in the middle. That's called the work energy theorem. And all it says is that the total work done on an object as it's being displaced from situation 1 to situation 2 is equal to the change in the kinetic energy from situation 1 to situation 2.